Hello, my name is Isaac Vashlewski, and this is my submission for the Flight Dynamics Unity coursework. The first part of the experiment was to determine sensible CG limits for the aircraft while the wheels were on the ground. If we look at the data collected from the Unity program, we can see how a range of moments calculated from the reactions acting on the wheels can be used to accurately determine the CG position of the aircraft. The graph shows a comparison of the true CG values and the calculated ones. Since the graph is linear and the trend line passes through the origin, it can be assumed that the CG values are virtually identical. For this aircraft, a CG of 0.1 units in the Z direction is suggested as the aft limit. This brings the weight of the aircraft back, while also leaving a large enough reaction on the front wheel to allow for control during taxiing. Next, we look at the thrust measurements of the plane. The Unity project is able to calculate the force that is being applied to the scale that an aircraft is pushing against. Since we have the RPM of the plane displayed in the top right of the simulation, we can plot the RPM versus the applied force. Increments of 10 RPM were used as it gives a good spread of data. 10 RPM was excluded itself as it created a zero net force on the scale. In order to match the controls given in this table, the elevator, aileron, rudder, and flap controls were all reversed in polarity using a polarity control function in the Unity project. For the longitudinal flight response, we had to verify the sign of the angle of attack and the elevator input were the same. We also had to examine the pitch response to the free-stream velocity and the pitch response for varying CG positions. The first pictures show the signs of the angle of attack are consistent with the signs of the elevator angle as requested. Next, the effect that wind speed had on damping was investigated. As you can see in the slide, a larger wind speed resulted in a higher damping on the aircraft in the longitudinal direction. Speeds of 10 meters per second and 27.7 meters per second were selected since these are the stall and maximum velocity speeds. The CG was also altered to explore the effect it had on the stability of the aircraft. From 0% to 15% of the Mach, the aircraft felt almost too stable and was difficult to gain altitude or move the aircraft in any direction. From 15 to 25%, the aircraft felt nicely manoeuvrable up to around 22% Mach before the other problems started to arise. From 25% to 35% Mach, the controls felt very sensitive and it was very difficult to control the aircraft. I also began to experience a strange roll phenomenon where the aircraft would suddenly roll to the left side for no particular reason. From 35% Mach plus, the aircraft felt almost impossible to control. For the reasons above, a CG positioning of 22% of the Mach was recommended. The next experiments focused on the lateral dynamic response of the Albatross, and this involved the investigations of the steady roll rate for differing aileron trims, the steady roll rate for differing wind speeds, and the damping comparison between pitch and yaw. Different aileron trim settings were applied to examine their impact on the roll rate of the aircraft. As you can see, the higher aileron angles resulted in a greater frequency of rotation and therefore a larger roll rate. The effect that wind speed had on the roll rate was also studied. Here, we look at the wind speeds of 10 meters per second, which is the stall speed, 18.9 meters per second, which was the cruise speed, and 27 meters per second, which was the max speed. As you can see, the higher speeds resulted in a higher frequency in the graphs, which means a larger roll rate. A comparison of the damping of the pitch and yaw was also investigated. As you can see in the plot, the pitch was able to normalise far quicker than the yaw was able to when the aircraft was destabilised using a manual input. Next, the effect that the location of the centre of gravity had on the thrust line was examined. It was found that when the CG is above the thrust line, upwards pitching moments were produced, and vice versa for when the CG was below the thrust line. A zero thrust pitch was created when the CG was around 2.7 centimeters below the y-axis. Next, the flight performance was examined using a static wind tunnel experiment in the Unity project. First, a plot of CL against alpha for different flap settings was made. Using the data collected from Unity, CL max was taken around 1.3, which is a little different when compared to the manufacturer's value of 1.5, however not so different for it to be a concern. A drag polar of the results from the static wind tunnel experiment was also constructed, as you can see on the screen. Finally, a lift over drag versus CL plot was made, and the best lift to drag ratio was just over 15. A plot of CM versus CL was also made to assess the longitudinal trim of the aircraft, as you can see on the screen. A plot of CL against different values of CM to obtain a desired CG position was also created. The ground handling of the Albatross was also studied. The video shows the Albatross working at 52 RPM and handling well. However, at higher speeds it began to lose control quickly and even flipped out at the higher speeds. Therefore, during taxiing it would be important to keep the speed of the aircraft to a suitable value. The maximum unstick speed of the aircraft without flaps was approximately 16 meters per second, as you can see in the video. With the use of flaps, the number reduced to about 14 meters per second. At cruise speeds, the trim angle required was approximately 2 degrees. Oops, sorry about that. If I skip through the video a little bit, we can get to the point at which I managed to achieve steady level flight. And if we move on to the next slide. For the minimum trim flight speed, we can move along the video a little bit further to get. Sorry, I don't know what happened there. If we move further along in the video, you can see that steady level flight at around 15 or 16 meters per second was achieved around 10 RPM. In order to achieve this, a trim angle of 17 degrees was used. For the maximum trim flight speed, you can see in the video that I managed to get to around 40 meters per second. In order to do this, a trim angle of -4 degrees was used to remain in steady level flight. The estimated long period, or the phugoid, of the aircraft was estimated using the phugoid experiment in the Unity project, and its final value was estimated to be around 10.2 seconds. Finally, the last video shows the flight taken around the pylons. The cruise conditions were met at times through the video, however I found it difficult to control at times, especially the large turns that were required at the edges. If I skip forward in the video a little bit. If I skip forward in the video, you can see me weaving between the pylons and trying to achieve a cruise altitude and speed, although not very well. If we skip along to the end of the video, you can see me landing in the hangar. And that concludes my presentation. Thank you for listening.